Good morning, everybody. Welcome to our machine learning seminar. Today, we'll have the pleasure to have a talk from Jan Sosa, who is a PhD candidate in the Department of Physics of the University of Luxembourg. But at the same time, he is a co-founder of a fancy AI startup, NeuralWave Technologies. Perhaps he will mention a few words about it. And today he will draw our attention to a particular mechanism that is a fundamental mechanism to many current state-of-the-art neural network architectures. So yes, Jan, the virtual floor is yours. Please go ahead.
All right. Thank you very much for the introduction, Jakub. It is a pleasure to be here in the machine learning seminar. And yes, today's talk is going to be about understanding the attention mechanism, which is one of the fundamental parts of modern AI and modern deep learning. So I think that it is important for us as researchers to actually understand what the attention mechanism is doing, so we can introduce it into our own pipelines. Also, I wanted to say that today's talk is going to be a bit more technical. So if you have any question, just turn on your microphone and ask me at any moment. There will be no problem, and we have time for questions. So don't worry about it. All right, so let's start. The attention mechanism is the basic building block of the transformer architecture. And I'm sure that most of you already heard about transformers. They are one of the most important inventions in machine learning in general. And they have single-handedly pushed forward almost every field of deep learning, from image generation to object detection to text translation and text generation. But before we actually understand transformers, we need to understand what the attention mechanism is, what it's doing, and how it was conceived in the first place. So that's the reason behind the presentation today. So how did everything start? Well, the research on the attention mechanism started when we tried to solve the problem of text translation, which is the task of translating one sentence from one language into another language. For example, let's assume that we want to translate this sentence, "We are learning attention," from English into Polish. Well, what we will do is use an encoder-decoder type of architecture. Here, the input sentence that we represent by a series of 4 vectors, x1 to x4, will get encoded into a latent space representation vector that we will then decode into the language that we want, which in this case is Polish. That's in a nutshell how it works. Nevertheless, in order for me to explain to you how the attention mechanism plays a role here, I need to explain to you in more detail how an encoder-decoder type of architecture works. So let's do that. Here we have an encoder, and the encoder is what we call a recurrent neural network. It is called recurrent because we use the outputs of the previous step in order to compute the outputs of the current step and future steps. So for example, here I have a vector that we call h2. This is the second hidden state representation of the encoder, h2. And in order to compute this vector, we will take as an input to a multi-layer perceptron, for example, the previous hidden state of the encoder and the current word that we are looking at, which in this case is x2. These 2 vectors will go as an input to this multi-layer perceptron, and the output will be a single vector that we call h2 here. Now, in order to compute h3, the next step of the encoder, we will take as an input the previous hidden state representation h2 and the current word of the inputs, x3, and so on. And we continue this whole process until we obtain the final hidden state representation of the encoder that we call h4. Now, in theory, all of the information about the input sentence is all contained inside of h4, but of course, in practice, this is not always the case. So now from h4, we can define another 2 vectors, S0 and C. S0 is what we call the initial condition of the decoder, and C is the context vector. Now, in principle, H4, S0, and C could be exactly the same vector. It doesn't necessarily have to be any difference between those 3 vectors, but nevertheless, we name them differently just because they fulfill different purposes, and we are going to see this now. So let's start the decoding process in order to compute the Polish words. The first thing that we need to do is to compute the hidden state, the first hidden state of the decoder, which we call S1. And in order to do this, we will take as an input to a multi-layer perceptron, for example, the initial condition of the decoder, the context vector, and a start token. The start token could be a vector of zeros. It doesn't necessarily have to contain any information. The only purpose of the start token is to signal to the decoder that the decoding process has started, and nothing more than that. So we have these three inputs, we will make them go through a neural network, and we obtain the first hidden state of the decoder, and from that we compute the first Polish word, okay? So now for the second Polish word, we will take as an input the previous Polish word, now the previous hidden state of the decoder S1, and the context vector, all the way here. And as you can see, the role of the context vector is to provide context to the word generation of the decoder. That's the purpose of it. So we continue doing exactly the same thing throughout the whole decoding process until the decoder outputs the stop token. And the stop token signals that the decoder has finished, that the whole sentence in Polish is already generated, so we can stop it. Here we can start seeing the main issue of this encoder-decoder type of architecture. The main problem is evident, and it is that we are encoding the whole input sequence, all of the information about the input sequence, inside of the single context vector here of finite size. And if we have a long enough input sequence, the issue is that it becomes harder and harder for the network to be able to actually compress all of that information into a single context vector. So the reason why the attention mechanism was developed on the first place is with the goal of solving the problem of losing information because of compression of the inputs. That's the whole reason behind attention, is to decompress the context vector. So now that we know why attention originated on the first place, I will explain to you how old attention works. And this is called old attention because it's the old way of doing attention. People normally don't use this anymore. They use attention layers. Nevertheless, I need to explain to you how old attention works, and we will move to the attention layer. But it's much easier to understand the attention layer if I first explain to you how old attention works. So I will go through the whole decoding process again, but by using old attention. Here we have the encoder, exactly on the same way as before. We have the 4 hidden state representations of the encoder, H1 to H4, and the initial condition of the decoder. Now here's where things get a bit different. So the first thing that we do in order to continue with the attention mechanism is to compute the alignment scores. The alignment scores are these 4 floating point numbers, E. So these are floating point numbers, these are not vectors. And this index behind below these alignment scores means different things. So the first subindex 1 here means that we are looking at the first step of the decoder, and the subindex 2 here means that we are looking at the second hidden state of the encoder, which is associated with the second word here, which is R, right? And the same thing for E14. First step of the decoder, looking at the fourth word of the encoder, which is attention. Now, so in order to compute these alignment scores, let's assume that we want to compute E14, we will take as an input to a multi-layer perceptron H4, which is the fourth hidden state of the encoder, and the initial condition of the decoder, through a multi-layer perceptron that the only thing that it does is to project those vectors into a single floating point number, which will be this alignment score. And we will use the same multi-layer perceptron throughout the whole process in order to calculate all of the alignment scores that we see here. So once we do that, we have 4 floating point numbers, and we make them go through a softmax function. The softmax function, the only thing that it does is to normalize the alignment scores. So it makes all of the alignment scores be bound between 0 and 1, and such that the sum of all of them is equal to 1. And from that, we get the attention weights. So the attention weights are just the normalized attention alignment scores. There is no qualitative difference between this set of numbers. So now that we have the attention weights, the next thing that we do is we multiply each attention weight by its corresponding hidden state of the encoder. So we multiply A14 by H4, and the same thing for all of the attention weights, and we sum them all up, following this formula here. which is the formula for the context vector. And this is the new way of computing the context vector. We can see that the context vector is now computed as the weighted sum of the hidden states of the encoder, which are weighted by the attention weights. And this is a qualitative difference compared to what we had before. For example, let's assume that for some reason, the network needs to pay more attention to the first English word in order to generate the first Polish word. So what would happen in this case is that A11 will be close to 1 and the other attention weights will be close to 0. So at the end of the day, the context vector will be approximately H1, which is the first hidden state of the encoder, which is associated with the first English word here. In that way, the network manages to pay attention to different parts of the inputs, depending on what it wants to generate. So after this whole process, we obtain the first context vector now. And from that first context vector, we proceed with the decoding process exactly in the same way as before. So in order to compute the first hidden state of the decoder, we take as an input the initial condition of the decoder, the first context vector, and the start token, and we generate the first Polish word here. Now, for the second Polish word, what we do is that we need the second context vector. And the way to calculate the second context vector is exactly the same way as before. It's just that in order to compute the alignment scores, we take as an input the previous hidden state of the decoder, which is S1. So if I go back one slide here, we will see that for C1, for the first context vector, we use the initial condition of the decoder to compute the alignment scores. Now we use the first hidden state of the decoder, which we computed in the previous step. And this is how we can sequentially generate different alignment scores and attention weights as we move through the decoding process. So we do this thing for the whole decoding process until we actually generate the last stop token for the decoder, and which signals that the decoding process has finished. So yeah, ask me.
Sorry, I will use that opportunity.
Good.
That you allowed for asking questions. So that means that alignment scores and attention weights, there are real numbers.
Yes.
And the number is a scale with the square of the length of the sentence to be generated, because you need to provide per each output, you need to provide the vector of alignment source that is proportional to the number of inputs.
Exactly. So the number of alignment scores is equal to the number of inputs times the number of outputs.
Okay.
So in this case, we have 4 tokens at the output, which includes the stop token. But it could be different, right? It could be, I don't know, depends on the language. It doesn't necessarily have to be a one-to-one number of words.
But in principle, the complexity, the memory complexity is quadratic with respect to the size of the sentence.
Yes, in principle, yeah. Just because of the way that language behaves in this case. So usually the number of output words is proportional to the number of input words. Okay, any other question? No?
I'm okay.
All right. So let me continue. So it turns out that by performing this set of operations, the network is much better at actually understanding and is much better at generalizing and training as well. And we actually solved the problem of the information compression in the context vector. But it has another interesting property, and that property is that we can actually look at the attention weights and learn something from them. So, for example, here I have an English sentence, and here on the top, and here in the vertical, I have the French translation to the English sentence. And here in the middle, I have the matrix of attention weights, which each column has the attention weights corresponding to that specific word. And we can see that most of the attention is paid on the diagonal, which makes a lot of sense. most of the translation is a word-for-word translation. So if, for example, if we look at the word August, we will see that the French translation is just the French word for August, which makes sense. Nevertheless, we will see this strange behavior here, and that is because the network managed to actually capture the word order inversion between English and French. And that's why we see a cross-diagonal component in the attention weights here. And this is a really non-trivial dependency. There is no engineer behind this, or there was no pre-processing of the data telling the network how the word order inversion works between English and French. Is the network was able to actually capture this dependency by itself, just by looking at vast amounts of data. And we can learn from this, right? Because you doesn't necessarily have to know this beforehand. But of course, this is a simple example of just text-to-text translation. But there are other examples which are much more visualizable than this, which is the example of image to text. For example, let's assume that we want to generate a caption of a given image. We want a caption that describes that image. So we will use an image to text network for this. And the way to use attention on this will be to, for example, take an image, make a convolutional neural network go through that image and generate hidden states that are associated with different parts of the image. For example, here H11 corresponds to the top left, the hidden states of the top left of the image. H23 is the hidden state on the middle right of the image, and so on. So now that we have a matrix of hidden state vectors, we can compute the the initial condition of the decoder as 0, and from that the alignment scores, exactly on the same way as before. Now the alignment scores go through a softmax function, and we obtain the attention weight matrix, which suffices that if we sum up all of the elements, this is equal to 1. And then, in order to continue, we compute the element-wise product between the attention weight matrix and the hidden state matrix, and we sum all of the elements up. It's exactly the same thing as we did before with the encoder-decoder architecture. So we do this, and we obtain the first context vector, and we start the decoding process. So we compute the first hidden state of the decoder by taking as input the initial condition of the decoder, the first context vector, and the start token, and this outputs the first word, which is smiling. Now, for the second word, we do the same thing, but we compute the second context vector. And in order to compute the second context vector, we will take as an input for the alignment scores the previous hidden state of the decoder. Again, the same process as before. And we can see that now the output word is man. So the whole decoding process output the sentence smiling man. The nice thing about this is that the attention weights now are associated with different parts of the image. So, for example, in order to generate the word man, the attention weights associated with C2 most likely have more weights right in the middle of the image. So most likely A222 will be approximately 1, and the other attention weights will be approximately 0. And that is why the face of the image is actually, the face of the man is actually in the middle of the image. So we can actually see where the network is paying attention to come up with the word man in this case. So let's see a couple of examples of this. So here are some examples of a network that works exactly like that. And we have on the left the input images, and on the right the attention weights superposed with the input image. So we can actually see where the network is paying attention to. And if we look at the word dog and we look at the attention weights associated with the word dog, we will see that the network is paying attention to the region in which there is a dog here, which makes a lot of sense, right? And the same thing for if we look at the word people, we will see that the network is looking at the people that are on top of the boat. And this is really, really non-trivial and useful as well. So, for example, if you are an alien and you do not know how people look like at all, the only thing that you need to do really is to train a network like this in a lot of data, and then see where the attention weights are paying attention when you highlight the word people, for example. And this is one way of actually obtaining information from just the correlations in your training data. So I explained to you how old attention works, and it is much better than what we had before. Nevertheless, it still has a small issue. And the problem is that all of the computations that I showed you are all serialized. So we always needed the previous hidden states of the decoder in order to compute the next hidden state of the decoder. So these are all serialized operations. And the main question that researchers had at the moment were, how can we perform all of these operations at once in GPU extremely fast, right? Taking advantage of the GPU acceleration and do not waste any time on calculations, essentially. And this is the reason why people come up with the attention layer. The attention layer is just the parallelized version of what I showed you before. And this is the modern way of doing attention. It's just the parallelized version of the old method of doing attention. And this is a simple schematic of how the attention layer works here on the left. And we will go through this schematic slowly. Nevertheless, I need to tell you that there are some simplifications in this schematic, and I will keep adding stuff as I go through the explanation, so it doesn't become overwhelming just all of the sudden. Also, I need to tell you that there is a change in definitions here as well. So previously we called the hidden states of the decoder S. Now we are going to call them Q, and they are here. And also we call the hidden states of the encoder H. Now we are going to call them X, and they are here. And the first step in the computation of the attention layer is to compute the alignment scores, exactly in the same way as before. And this is this matrix E here. Now these are called similarities. They are not called alignment scores anymore. There is no reason why they changed their name. It's just that people call them differently. There is no reason behind it, but it's just called similarities now. And let's assume that we want to compute E31, for example. So what we will do is we compute the inner product between X1 and Q3. So now all of the similarities are just inner product between vectors, which is a really fast operation. So we compute all of those inner products and we obtain this similarity matrix. We will make them go through a softmax function that now acts column-wise. So the softmax function acts column-wise. So that means that if we sum all of the elements of the one column, it will be equal to 1. And the same thing for the second column, the same thing for the third column. And in order to obtain the outputs y, we need to do simple tensor operation. So we need to multiply the attention weight matrix A by the inputs X, and we obtain the outputs Y. So as you can see, these are all extremely fast operations to be performed on a GPU with tensor acceleration. But still there is one small issue here. The issue is that there are no trainable parameters in this whole schematic. So there is no way for the network to train anything here. It's just inner products and a softmax function and tensor operations. So what is the easiest way to introduce learnable parameters to the attention layer? And the easiest way is just to introduce trainable weight linear transformation matrix. So we introduced these W matrices, WK and WB. WK, the purpose of WK is just to transform the inputs X into the vectors K. And the way to do this is just to multiply X by WK and we obtain the K vectors. It's just a simple linear transformation. The same thing for the B vectors. They are obtained by multiplying the inputs X with the weight matrix WB. And that's it. It's just a really simple way of introducing trainable parameters. Everything is linear here. And also one thing that I need to explain here is that, as you can see, we call these vectors in a very suspicious way. We called it Q, K, and B. And the reason why we call them Q, K, and B is because in reality, the names are queries, keys, and values. There is a reason why. I'm sure that most of you already heard about queries, keys, and values. And if you work with attention, you are going to hear about queries, keys, and values all the time. And the reason why is that it is said that the attention layer behaves like a retrieval system, like a dictionary search. For example, if you search for something on YouTube, you will type something in the search bar. That will be your query to the YouTube algorithm. then the YouTube algorithm will search for matching keys in its database, which are the tags of the videos. And it will give back to you a list of videos that you will hopefully like to watch. And those are the values. So that's how a retrieval system works. And it is said that the attention layer is doing exactly that. It is retrieving information with the queries, the keys, and the values. Now, in reality, there is no mathematical demonstration. There is no proof of this. It is just an analogy, and people should go with it. And this sometimes confuses some people because in reality, there is no retrieval algorithm here. It's just you need to know that this is just a set of tensor operations, and that's it. And these are called queries, keys, and values. Now, another thing. So I introduced these queries here, but I never explained to you where they come from. So the different sources of the queries determine the type of the attention layer that we're looking at. And there are two main types of attention layers. There is the self-attention layer and the cross-attention layer. And in the self-attention layer, which we see here, the queries comes from the inputs themselves as well. So we have another trainable weight matrix, WQ, which performs a linear transformation on the inputs, and that allows us to come up with the queries. That's why it is called self-attention, because it is said that the inputs X are paying attention to themselves. That's what is said, right? And for cross-attention, the queries come from elsewhere. And elsewhere could be absolutely anywhere. It could be a set of vectors that you have already defined somewhere, or it could be another piece of network. That's why it is cross-attention. It is taking the attention mechanism and crossing it to another different part of the overall architecture. Okay, so
sorry,
yeah.
Sorry. And you can get back. This multiplication that we have here, the trainable one, this is just a point-wise, like x1 multiplied by a single number, or you have the matrix vector multiplication?
You have the matrix vector multiplication. It is defined here.
I see. So the W is a matrix and X is the vector of X1, X2, and X3, right?
Yep.
Okay, thanks.
Right. Any other question? Okay. So, okay, let's continue. So the attention layer is actually pretty simple. Everything that I explained to you about the attention layer is here on this slide. On the left, we have the trainable parameters. This linear transformation matrices, WQ, WK, and WV. These are all the trainable parameters of the whole attention layer. And from here, we obtain the queries, the keys, and the values, right? Just by performing a tensor multiplication, and that's it. And here on the right, we have all of the operations of attention using the queries, keys, and the values, all represented in this simple formula. So the queries get multiplied by the keys. Then we use a softmax function in order to obtain the attention matrix. And then the attention matrix is multiplied by the B matrix, and we obtain the output set. So all of the operations that you need to perform are here on this slide. And the attention layer is actually pretty simple to program and to use. But that's not all. There is another issue here. And the issue is that usually correlations have different origins. They can be qualitatively different. For example, let's look at this sentence here, which reads, "This restaurant was not too terrible." The word terrible here is a property of restaurant, but also the word not inverts the word terrible, and the word too moderates the word terrible. So, and these are all correlations between words that have completely different qualitative meaning, right? And it will be good for us to actually differentiate between all of the different types of correlations that there are in the network. And that is the purpose of multi-head attention. So it sounds difficult, but in reality, multi-head attention is pretty simple. The only thing that you need to do actually is to cut your inputs in the embedding dimension to essentially have more inputs now. And you give one piece of the inputs to one attention head, which is one attention layer, and another piece of the inputs to another attention layer, which we call another head. And these heads have different weight matrices. So the attention head number 1 has the matrix W1Q, W1K, and the attention head 0 has W0Q, W0K, and so on. So by doing this, we perform multiple attention layer operations in parallel. The problem with this is that at the end, we will obtain multiple outputs, right? Because if we have 8 attention heads, then we will have 8 outputs. And in reality, we will only like to have 1 output from this whole structure. So what we do in this case is we simply concatenate all of the outputs from the attention heads, which are set 0 to set 7 here. And then we multiply by a linear transformation, by a transformation matrix that just makes all of those outputs and reshapes them into into the dimensions and sizes that we want. So this is only a reshaping of the outputs. And this is a trainable weight matrix, W0. So all of the parameters of this matrix are trainable. And it is said that W0 learns how to do a consensus of the attention heads. But of course, this is just an analogy. In reality, this is just a set of tensor operations, right? Okay, and that was the whole attention, self-attention and cross-attention and attention heads. And at the end, I wanted to show you how to implement this in PyTorch. This is a PyTorch implementation of self-attention absolutely from scratch. And as you can see, it's actually pretty simple to do. Everything that I explained to you is here in just this couple of lines of code. So it is pretty simple to implement and also pretty simple to modify. There has been a lot of work recently just by modifying attention a bit in different ways and introducing different loss components into different parts of the attention as well in order to improve training and so on. So it is something to experiment for sure. But you can also use the native PyTorch implementation of multi-head attention, which is 2 lines of code. Here you call the multi-head attention neural network, and you define the number of heads, and if you're going to use cross-attention or self-attention and all of the stuff that we need. And that's it. So that was pretty much it. Thank you so much for listening. If you have any question, you can ask me.
Thank you so much, Jan. It was indeed technical, and I believe that there can be many questions to ask. I have several, although I can understand that it was quite fast. The pace was quite fast. So if somebody is not really experienced in those kind of architectures, it is easy to get lost when hearing this for the first time. Yeah. Hopefully, happily, the presentation has been recorded, so one can hear it again and read more. But may have some questions for the beginning.
Yes.
And then I will let others to ask their questions. So I will just start with a single one. So you introduced the softmax at some point, right? As a way to normalize this alignment scores to attention weights. And my question is, what's the reason for using softmax to normalize instead of, for instance, some linear normalization? What's the idea behind this, and what function does it do? And maybe some sort of extended question, is it somehow related to the fact that otherwise there is no nonlinear transformation except this one in the whole network? Or maybe you simplified this and you haven't provided the activation functions that maybe are there, but normally I couldn't see anything nonlinear except the softmax.
That's a very, very good observation there. Yes, there are no nonlinearities apart from the softmax function, actually. Everything is linear. When you use the attention layer, you need to add your own nonlinearity. So ReLUs and all of that, you need to add them either before or after the attention layer, because otherwise there is very much non-nonlinearities here. And so continuing with the question, there are a couple of reasons why you want to use softmax function. One of the reasons is the gradients. Otherwise, if you don't use, so the softmax function is built in such a way, it's also normalized in a particular way, so that the gradients more or less remain, have the same norm through the whole process, and they don't explode or they don't go to zero when you have long input sequences. And but the main reason why we use softmax is because usually these types of networks like expressivity a lot. And by expressivity, I mean that the attention weights like to be extremely big and very well defined. So if you have fuzzy attention weights, it becomes extremely difficult for the network to actually learn something. And what the softmax function does is just that it really highlights the maximum alignment scores by a lot and makes the other alignment scores close to zero. It is actually called softmax because it's a soft version of the max function. The max function returns a 1 when it finds the maximum element of a given input sequence and 0 otherwise.
Okay. Any questions from the participants?
Maybe I can go. Hi, Jan. Thanks for this nice presentation. I wanted to ask you that did you deliberately choose not to touch upon the positional encoding part?
Yeah, you're right. Yes, I deliberately choose not to do that because if I do that, then it really becomes extremely much more confusing. So I can explain to you a bit about the positional encodings. So let's look at this for 1 second. Maybe some of you picked up on this little issue here. The issue is that when we perform this set of operations, when we sum up all of the weighted hidden state vectors, we lose information about the order of the sequence because the summing up elements loses information about order. You don't know which element was first and which element was second, and so on. So in order to solve this problem, what people do is they introduce positional encodings. And positional encodings essentially is a piece of vector that you concatenate into the hidden states that encode the position in the sequence. For example, H1 will have a 1 encoded, H2 will have a 2 encoded, and so on. That's a way to actually introduce information about order into the hidden states themselves, so that the summing up of the hidden states doesn't lose the information about the order.
So I wanted to ask that when you said old attention, and do you think that, I mean, have you come across the literature that do they also emphasize on positional encoding even in the context of the old implementations, or it's just very particular to the recent transformers, I mean, the recent attention?
No, it's more particular to the recent attention. Actually, I don't think it was so prevalent in all the attention, but it's definitely something that it is a mandatory thing to do with the attention layer.
Mm-hmm. I also recently came across some papers. I'll send it to you that which also try to say that maybe even no positional encoding works better than the positional encoding because you fix it on the kind of transformation that you want to have.
Yeah, I agree with that. I mean, there are some cases in which you will actually do not want to introduce any positional encoding because you only care about the behavior of the distribution of inputs, for example, and not about the order of the inputs.
Okay.
That could be one of the main reasons why not to use positional encodings. And nevertheless, honestly, I'm struggling to think about any system in which you care about only the distribution and not about the order of the inputs as well. So it will be great to have a paper if there is some example like that.
I think, yeah, we should talk about this, because maybe there can be something done in terms of defining. I already talked about this, I guess, long back, that
Yep.
maybe we could come up with smart positional encodings that's very particular to kind of problems we deal with, for example, mechanics, or it can be nice, I guess. I
Yeah.
have seen such papers.
Yeah, I mean, it is an important part. There are different ways of doing the positional encoding for sure. It could be a trainable, it could be a fix. There are some functions that also define the position that are used in the GPT models, which are deterministic, for example. And it's worth, I think it's something worth trying out for sure.
Yeah. Okay, thanks. Thanks for the
Yep.
nice brief introduction.
Jan, maybe last question from my side, because you haven't mentioned about the training of the network, right? So we bring up some particular architecture because usually it is about the training of the network and how capable it is to handle the complexity of the dependencies in the data.
Yep.
And the capability of it trained in a reasonable resources, and also find the minimum or the fitting more easily with the method, optimization method that we use.
Yep.
So can you somehow comment on that, how this particular complex architecture that we are using here is suitable to the training procedure on a given data, and what data are we expecting the input output?
Yeah. So in principle, one can use the attention layer to do whatever you want. So it doesn't necessarily have to be sequence data in principle. So I've trained attention-based part of architectures that have nothing to do with translation or text generations and so on. Nevertheless, training sometimes can become a bit difficult when training the attention layer and the attention mechanism. It's just because that the network is trying to find, in principle, infinitely ranged correlations in the inputs. So in principle, there is no real distance between the inputs. So it's trying, by modifying these parameters, you are trying out to see all of possible combinations between paying attention to different parts of the inputs and what can work the best. So there is no restriction about where the network can pay attention to. And this could be an issue for situations in which you know that more or less the network should pay attention to a given region. For example, let's look at this. Here you know that the network needs to pay attention to more or less the diagonal. So you know that the attention weights should be bigger towards the diagonal. And this could be a really non-trivial thing to figure out for the network sometimes. So what happens is that it seems like the attention layers, if your inputs are too big, sometimes it is difficult to train it because it never finds what is the sweet spot of where to pay attention to. And one of the ways to actually solve this issue, and something that I've done in the past, for example, is that if I know that the attention weights should look more or less in some way, like for example, here we can assume that the attention weights should be more or less in the diagonal, you can introduce a component of the loss function that will push the network to pay more attention to the middle. Like for example, imagine a loss parabola here that is centered on the diagonal that will push the network to pay more attention to the diagonal elements of the attention weight matrix. And you only turn that loss component into the beginning of the training procedure. So the network actually learns to pay attention there, and then you turn off that loss component so that the network can fine-tune all of the attention weights. So yeah, it can be a tricky thing to train, actually, an attention layer.
So in general, it is a kind of combinatorial optimization.
Yeah.
Not a continuous one in which you have some well-specified as finite number of minima.
Exactly.
Here you can expect anything.
Yeah.
That can happen.
Yeah, essentially the loss landscape becomes extremely complex. It is sometimes extremely difficult to find a proper solution. So the optimizer gets lost in the beginning of training a lot of times.
Right. Thank you, Jan. I can see no other microphone switched on, so I assume that there is no more question. Thank you again for your time to prepare this presentation, and I believe that it will serve to us all as it will be published online. So thank you again, and thank you for your attention.
Thank you.
And I will keep you posted for the future machine learning seminars.
Yep.
In the incoming weeks. Bye-bye.
Bye.